is Ronan Legin from University of Montreal, talking about simulation-based inference of strong gravitational lensing parameters. Ronan, please take it away.
Okay, thank you. You can hear me well? Good?
Yes,
okay.
Loud and clear.
Okay, great. All right, so hi everyone. So yes, my name is Ronan. I'm a first-year PhD student at University of Montreal. And so what I'll be talking about today is how we're using neural networks to perform a strong lensing analysis and to figure out how we could robustly model their error or their uncertainties. And oh, hold on. Okay, good. So first, I'll quickly go over strong lensing and some of the challenges that come with the upcoming surveys. I'll talk about how machine learning can help resolve some of these challenges. And finally, I'll talk about a kind of new project I'm working on, which involves population inference of strong gravitational lenses. So I'm assuming by now you probably know very well what strong lensing is. So it's basically this gravitational distortion of the light from a background source that causes multiple images of this background source. And so you also know how strong lensing can be used for important applications in cosmology. For example, we can use them to learn more about the distribution of dark matter in the foreground galaxy. And we can also use them to obtain estimates of the expansion rate of the universe through what is called time delay cosmography. But before we can use strong lenses for any sort of scientific application, we first need to characterize the lensing system itself. And so this comes down to reconstructing the background source of light and the main lens causing the deflection. And in the previous talk, you must have seen that when you might have if the source and the main lens deflector are fairly complicated or irregular, then you could model them on an image over a pixelated grid. And as Alex showed us, this would be the case for the famous cosmic horseshoe lens. But in many other scenarios, cases, where both the source and the main lens galaxy are simple, regular galaxies, you could model them with parametric models using several key parameters. And so the task of analyzing strong lenses in this scenario boils down to predicting these parameters. So now, in the next few years, with a new generation of sky surveys, for example, LSST and the Euclid Space Telescope, are estimated to discover hundreds of thousands of new strong lenses. And so this provides an exceptional opportunity for all science applications based on strong lensing. But at the same time, we now have the great challenge of having to characterize all of these lensing systems. And if we were to do this using traditional methods, which can take a couple of days sometimes to do on one lens, then this could take thousands of years to do for all of these lenses. And so we need to find a way that can rapidly predict these strong lensing parameters, but at the same time provide accurate uncertainties on these predictions. And so now I'm going to talk about how this can be possible using machine learning. And so in recent years, convolutional neural networks have been shown to be a very powerful tool when it comes to predicting strong lensing parameters. And in particular, they have shown to be orders of magnitude faster than traditional methods, and they have even been used on real data to great success. And so nowadays, CNNs have become a staple in strong lensing. But the problem is that in their basic form, they only predict point estimates of lensing parameters and are devoid of any kind of uncertainty on their prediction. So how do we model the uncertainty of these CNN predictions? In other words, how do we perform posterior inference based on these CNNs? And so I'm going to talk about how we could do this with what's called simulation-based inference, or also known as likelihood-free inference. And it's basically, simulation-based inference is basically a statistical framework where you might not be able to explicitly evaluate the likelihood, but you might be able to generate realistic simulations and use that to do inference. So your simulator, you can look at it as a kind of implicit likelihood. And before going more into detail, I just want to go back and traditionally what we do. So we do likelihood-based inference, where you will sample from a strong lensing model parameters from an MCMC, run it through a simulator, and get a model for your lens. And then you're going to compare this lens with the real lens you're interested in through an analytic likelihood function. And so, so there's a couple issues with this because it's known that it's pretty computationally expensive, and that the analytic likelihood function sometimes might just be, well, often it's an approximation to the real noise and systematics in your data. So in a case where perhaps, I guess you don't have an explicit likelihood function, you could do this alternate kind of setup where this is likelihood-free inference. And here you would basically sample a bunch of model parameters from a prior, run it through a simulator, but here you add noise to your simulations that mimics the real data. And so you get your strong lensing simulations. And often you would compress this because the images are technically high dimensional pixel-wise. And so you could like, so you would compress this and you could compress this using, for example, a CNN that predicts strong lensing parameters. And the idea here is that you would keep the model parameters that resulted in compressed statistics that are close in distance to the ones from the observed lens, the lens that you're interested in. And so these samples that you keep would be samples from the posterior. But this whole setup, which is known as approximate Bayesian computation, you have to regenerate all these simulations basically every time you want to infer a different lens, which would be not tractable for these upcoming surveys. So we could look beyond ABC within this realm of like simulation-based inference, as there's different methods that we can use. For example, I show a figure here of various setups, and one of these is ABC. But I want to pay attention to the bottom row, where these are classified as amortized inference. And amortization basically just means that you would train or learn a model, like for example, a neural network, to do posterior inference. So you train it first on many repeated simulations of your problem, and then you could do posterior inference efficiently on many different observations in a computationally efficient way. So we're looking at these methods to solve the previous problems. And for example, you might recognize amortized posterior, which could be, for example, a neural network that directly predicts a posterior distribution on strong lensing parameters. And often an example of this is Bayesian neural networks that have been often used in the past for strong lensing. But I want to go to the method right beside it, which is called amortized likelihood density estimation. So here you're learning, you could use a neural network to learn to predict the likelihood, and it's trained from many simulations that you generated, realistic simulations. And so, so basically, so why would we want to learn the likelihood versus doing, let's say, Bayesian neural networks or amortized posterior? It's because the likelihood is independent of the prior. And so the neural network, when it's training, does not need to implicitly learn the prior in the case of if it's learning the posterior. And if you learn the likelihood, then if you use it with an MCMC, then you're free to choose whatever prior you want. And this is great because the prior can be arbitrarily complicated, which would make the neural network training even more difficult in the case of amortized posteriors. And so now so if we're doing amortized likelihood, basically we're using a neural network to predict a distribution over our data. But since our data is like high dimensional images, technically, this is intractable. So what I do instead here is that I'll learn a likelihood over compressed statistics of the data. So this would be CNN predictions of strong lensing parameters. And so you learn this likelihood from a training set of simulations. And then once you have this likelihood, you can sample from a posterior over strong lensing parameters using an MCMC, for example. So just to go back on that, so how would we learn the likelihood using, let's say, a neural network? So first, you would sample a bunch of model parameters from a prior. Then you'd pass these model parameters through your simulator to generate realistic, noisy, strong lensing images. Then you'd pass these images through your kind of a compression step, where here it's a CNN that predicts strong lensing parameters. And then you would gather the compressed statistics and the model parameters in this joint space, where you're going to finally model the density, a conditional density representing the likelihood. So you can model it with like a parametric density model or something like that. So specifically, so for my case, how do I model the likelihood? So I use what is called a mixture density network, which is a neural network that predicts a analytic parametric distribution. And so the distribution that it predicts is a Gaussian mixture distribution. So basically, it's going to predict like a mean and covariance of these Gaussian components representing the distribution of the likelihood. And so we train this neural network, just like any other neural network, and we train it with about 100 million strong lensing simulations that we generated. And once trained, so it gives us a prediction for a likelihood. So what we can do to do posterior inference now is that we can use its prediction of the likelihood combined with MCMC to sample from the posterior. And before doing this, we have our lensing image on the left that passes through a compressor to obtain our compressed statistic. And then we evaluate the likelihood at this compressed statistic. And so that's what we did. So we use our mixture density network to infer 100,000 different posterior distributions from 100,000 strong lens simulations. And sampling all these posteriors takes about 2 days with a single GPU. So it shows that this method scales pretty well to the large number of lenses that will be discovered in the future. And once we got all these posteriors, we want to verify if they're accurate. So what we did is this coverage probability test, which is basically just checking how well your posteriors are covering the true simulation values that were used. And so this result here gives a sense of underconfidence and overconfidence in your posteriors. And the diagonal line is perfect coverage. And we could see our method, which is the red line, does pretty well at obtaining accurate posteriors. And we also compare with a result from a BNN that appears to suffer a bit from underconfidence in its predicted posteriors. So now looking forwards from this, I'm interested in using this neural network likelihood model that I trained to do population inference of strong lenses. And for example, a simple like a population problem can be written kind of in a hierarchical framework like this, where we could easily plug in our own like likelihood, neural network likelihood in this equation and perform the inference. And the great thing with this is that you only need a CNN, the value of the CNN compressed statistic to evaluate this likelihood. And it's basically a matter of evaluating a Gaussian mixture distribution, for example, in my case, which is extremely fast and easy. So this, in a sense, could allow population experts to perform their own hierarchical inference task without necessarily being an expert in strong lensing. But I want to go a bit further, and I want to do this population inference by taking account selection bias. So in this case of selection bias, so the set of data that you use to infer the population, it could be a biased kind of sample from the true population of strong lenses. And this is because your detection process might have an easier time detecting certain strong lenses versus others. So you don't have a complete sample set like representing the full population. And so a way to kind of correct for the selection bias is through a normalization factor that's going to depend on, oh, so I forgot to mention, lambda here is population hyperparameters that just describe the population distribution. So we add this normalization factor in the denominator that will essentially correct for the selection bias by reweighting the posterior over the hyperparameters of population. And so you could think of it as like the fraction of samples that would be discovered given a certain population distribution. And specifically, how to write it out. So this normalization factor is an integral over what is a probability of detection of strong lenses with certain model parameters times your population distribution. And now the difficulty here is to evaluate the alpha, the normalization factor, because it's difficult to evaluate this normalization factor because the probability of detection is often unknown or very complicated, right? So this P of the detection, it depends on the detection process. And if, for example, I use a CNN lens finder for the detection method, well, it's essentially a black box. So it's difficult to know when it fails and when it succeeds at detecting certain types of lenses. So this is a project I started working on recently, where I use neural networks to predict this probability of detection. And so basically, the idea here is you could use a neural network to classify between a set of model parameters that result in a detection and another set that does not result in detection. And so this is a simple neural network. And to generate the training data of this neural network, you would apply your whatever detection process, selection process you're using on a bunch of simulations. And then you would just gather the lenses, the model parameters of the lenses that were positively detected as strong lens and the ones that were negatively detected. And so this is how you would build up your training data for the previous classifier. And so then we did an initial test where we're trying to infer the population of Einstein radii from a biased set of 1,000 strong lenses. And the population here is a simple log normal distribution with a mean and standard deviation as hyperparameters that we want to infer. And here are preliminary results where we show in red the posterior of the population hyperparameters when we take into account this bias correction, and in the blue where we don't take it into account. So we can see that the neural selection function that we trained, this classifier, is necessary for this case to perform unbiased inference. And so with that, I'll quickly summarize if I have time. So we use density estimation to model the uncertainty of CNN predictions of strong lenses. And so I also, as a side project, I'm trying to use neural networks to learn a correction for selection bias in order to perform a population inference. And so with that, I'll share a couple of links to papers, and feel free to send me questions by email, and I'll say thank you. So,
thank you very much, Ronan. Questions from the audience? I look a bit around to see some. I see some senior people, some junior people I see also.
Thank you. That's really great work. I was just wondering about this correction for selection bias, because of course we would ideally like to do it with real surveys as well. So do you have any idea how we might be able to estimate this for real LSST data, for example?
Yeah, so the idea is that, so I hope I understood the question right, but like the idea is that whatever you train your neural selection function on, you have to make sure that the simulation, the strong lensing you train it with the noise and all that, the statistics are representative of whatever real data you want to apply it on. So if you're going to apply on LSST data, you have to make sure your strong lensing simulations have similar noise properties. And yeah, in that case, or else you might have to retrain a new network for different noise properties or types of simulation. Yeah, I'm not sure if that answers. Sorry.
Yeah, that answered it. Yes, thank you.
Okay, great. Thank you.
Any other questions? Yeah, Gautam.
So sticking with the question on the training data, especially when you try to move to a hierarchical model, the training data itself is an implicit prior, right? Because you have a million objects, and what's the distribution of those objects? At some level, there is some implicit prior there. How does that change amortized inference in the hierarchical case versus when you only have a single system?
Right. So I would say that, like, again, how does that change? So I think, like, so from what I know on this, I started recently, is that so the implicit kind of prior in this would be like whatever you train your neural networks on. So you'd want to make sure that like the prior you use to generate your training data for these neural networks is the same prior that you would in like once you apply it in the real life scenario. Or else if you do that, then yes, you could end up with like kind of biased inference. But that compared, so that compared to the individual strong lensing analysis, in that case, what's great is that for that, like the prior, since you're modeling the likelihood, it's really the prior is independent. You just have to make sure that your neural network model that you train to learn the likelihood has support for all the kind of prior model parameter samples that you could get from your prior.
And how well do we think we know the prior distribution for lens systems going into the training set?
Oh, that I'm not sure. That's something I have to figure out still. So yeah, sorry, I don't know exactly that question, the answer.
If I chime in, this is basically what Gautam asked is a very similar question that I asked Alexander before. It's like what you put in a in your training set. We cannot probably assume that we know the universe is always surprising us. There is work that actually divides out your interim prior into the simulation. And given you have analytical form, you can divide out the prior when you do the population level inference. So one work that's been done on simplistic data or simplistic mocks is Garena Wagner et al. 2021, who did this in strong lenses. Yeah, I think it's technically possible also if you're dividing out the prior while doing the inference.
Yes, yes.
As long as you're not dividing almost to 0, so numerically dividing out is challenging.
That's it. There's some numerical instability that could occur, but
yes,
that's the issue with. That's the thing with simulation-based inference is you have to make sure your simulation are representative of reality. So yeah, that's the difficulty.
Other questions, comments? I look at the Zoom. Let me 1 second. No hand is up. Any other question, comments for Ronan? Otherwise, let's thank Ronan again. It's a great talk.
Thank you.
And we move from virtual